You're welcome.
And let's move to the last paper of this session, who will be presented by Cristiano Pegoraro Chenet, who will talk about using analog scrambling circuits for automotive sensor integrity and authenticity. Cristiano Pegoraro is a PhD student in computer and system engineering at Politecnico di Torino in Italy. He works with cybersecurity and deep learning and has more than 10 years of experience in hardware engineering in the Brazilian industry. Thanks a lot, Cristiano. You can go ahead.
Okay, are you hearing me?
Yeah.
Okay. As Marcello told us, my name is Cristiano Chenet. I am a PhD student at Politecnico di Torino. This work was developed by me and the professors Alessandro Savino and Stefano Di Carlo. This work continues to discuss the previous work that my colleague Frank presents, that is about the cybersecurity in the automotive domain. The title of this work is Using Analog Scrambling Circuits for Automotive Sensor Integrity and Authenticity. The overview of this presentation is the introduction, the proposed architecture, the implementation, simulation setup and procedures, results, and finally the conclusions. The amount of hardware and software embedded in the automotive domain is rapidly increasing. The electronic systems in modern vehicles can be separated into several electronic control units, ECUs. As we can see, we have an example of ECU in this figure. The ECU can be implemented by a system on chip or also in a microcontroller, and connected to it, we have sensors and set point generators and actuators. The cybersecurity concern with these automotive systems led some authorities to release regulations for the cybersecurity of vehicles. As example, we have the UN R155 and the UN R156 regulations. The first requires a management system that focuses on cybersecurity during the entire vehicle life cycle. And this specific regulation is interesting for us because it takes care about the security of the information collected by the sensors. And the previous presenter, Franco, told us about the validity of this regulation that is starting this year. Some sensors strongly impact the engine performance and may be of particular interest for attackers. These sensors are the mass airflow sensor and the fuel rail pressure sensor. Both these sensors have resistive characteristics, and they are connected to a ECU called Engine Control Module, the ECM. To increase the engine power, some attackers use tuning boxes. As we can see in this figure, in the point 1, what the attackers do is they disconnect the sensor from the ECU and connect between both the tuning box. This type of attack characterizes a man-in-the-middle attack. And it's very important to the car makers to be protected against this type of attack to save costs and protect their reputation. In this scenario, this paper proposes a novel architecture to secure the communication between analog sensors and the corresponding ECUs. The proposed architecture is focused on integrity and authenticity. Integrity means ensures the information is trustworthy and free from tampering. And authenticity has as a goal ensures that the data originates from a trusted source. This architecture was designed to comply with the following requirements: implemented using standard commercial electronic components, modify as little as possible the design circuit, be low complexity and cost solution, and guarantee a fully analog sensor component. The proposed architecture was based on a hard-to-invert exponential function, and we have a block diagram of this in this figure. It is composed basically by a hard-to-invert function, exponential function, and this function receives the sensor signal and also an analog secret key. These two sensors, these two signals, they modulate the exponential function that generates a signal that we call analog signature. The ECM receives this analog signature and receives also the sensor signal that, as it is nowadays, is an uncovered signal. Also, the ECM previously knows the secret key, and it can compute in the digital domain a parallel value of the analog signature. Therefore, the integrity and authenticity verification are performed by the comparison between the analog signature signal and the digital computed signature. About the implementation, I will start talking about the first block, the generator of analog secret key. It uses a weak physically unclonable function. The electrical parameter chosen to generate the secret key is the input voltage offset of an analog of an operational amplifier, and this offset arises due to unavoidable variations present in the differential pair of the operational amplifier input stage. And in the low side of this figure, we have this differential pair input stage of the operational amplifier, and the offset is generated in this circuit. The hard-to-invert exponential function is based on the IC versus VBE curve from bipolar transistors. In the range between 0.5 and 0.7 volts, the curve is a well-characterized exponential function. And therefore, we use this feature to implement this exponential function. This architecture was implemented in LT SPICE based on commercial operational amplifiers. In this graph, we have the DC simulation of the analog signature. We can see the behavior of the analog signature versus the secret key behavior, and also the sensor signal behavior. We can see that the analog signature is has as a behavior an exponential function. Simulation setup and procedures. Besides the device under test, we also implemented an auxiliary device. It is composed by a noise injection block, an attack injection block, and scrambler similar to the scrambler in the proposed architecture in the device under test. The procedures, they are basically divided into the number A, the first, is a noise injection and attack threshold determination. And the second is the attack detection analysis. The noise injection and attack threshold determination, the idea is the following. The goal is to inject noise on the Dutch sensor and determine the maximum difference between the Dutch analog signature signal and the auxiliary device analog signature signal. This value will be the attack threshold, that is the minimum difference detected as an attack. The second procedure, the letter B, is the attack detection analysis. The goal is to determine the smallest amplitude change of the sensor signal detected as an attack. Regarding the noise injection and attack threshold determination, it was performed by enabling the noise injection block, and this block generates a white noise with a peak amplitude of 3% of 4.5 volts. That is the full range value of the sensor. And we choose 3% because this value is the sensor error margin. We perform the simulations, and as we can have in this graphical, we have 3 pairs of signals, and each pair has an analog signature with noise and also an analog signature without noise. In this case, the maximum difference between the signal with noise and without noise is the threshold, the attack threshold, and we measure it as near 31 millivolts. Therefore, this was the attack threshold defined. Regarding the attack detection analysis, it was performed by adding a crescent linear voltage to the sensor signal. In this graph, we can see the exact moment of the attack. The attack threshold was exceeded, and in this moment, this occurred when the signal injected by the attacker was near 47 millivolts. That is near 1% of the sensor range. This result shows a reasonable capacity of the architecture to detect attacks. And finally, the conclusions. This paper proposed the first step forward by offering a new security architecture to generate an analog sensor signal signature. Preliminary simulations using LT spice models proved the proposed approach's feasibility in detecting the signal tampering. And of course, additional work is required. The first may be prototyping the architecture to better assess the stability of the analog signal generation. And also, we may implementing full analog one-way functions that can further increase the security level of the solution. Thank you very much for the attention, and is this.
Thanks a lot, Cristiano, for your very interesting presentation. So are there any questions from the audience for Cristiano? Okay, I don't see any. Okay, maybe I have one question for you. So at some point you said that your ECM already knows the secret, right? That the sensor is supposed to use to generate the signature, if Perfect. I'm not mistaken. Yeah. Can you detail a little bit on that? I mean, how is this done in practice?
Yeah. In fact, we didn't explored a lot this point. But for example, a way to do this is record the analog signature for each device, and store this recorded signal inside, of course, in the digital domain inside the ECM. This is a possibility. Basically, this.
Okay, but what do you think would happen if the ECM is? I mean, when you don't have much control over the ECM, meaning that you maybe bought it from someone else, from some vendor, and I mean, you have to trust the vendor, right? So this could actually be a problem for you, right?
Yeah, if I understood, what I imagine is that should be a match between the ECM and the sensor, or the sensor system, in this case, the sensor with security, and should be like a pair between both. I think in this way, and of course, for example, if the sensor breaks, it is necessary to maybe reconfigure the ECM for the new sensor.
Yeah, because this is some kind of symmetric key sharing between the two the two parties. Do you think it would be feasible to put in place something which is not symmetrical, meaning something that creates keys on the fly, or would it be too much a pain to do this?
Do you mean in order to could change the pair ECM and sensor without a lot of work, right?
Yeah, at some point you could change keys transparently, so that in this way the communication is more secure, because you're changing keys, and an attacker could not, let's say, sniff or understand your key in some ways.
Perfect. I understood. I think that maybe this is a weakness of this architecture, and we may improve this in the future, but we need more work in this point. Yeah,
of course. Okay, thank you very much for your answers. Are there any other questions for Cristiano? We may have another minute. Okay, I don't see any. Okay, if